It is intriguing that female reproductive organs develop from the same unisexual primordia as those of males, with certain hormonal influences in early development determining whether certain primordia become ovaries or testes, clitoris or penis, labia or scrotum. The genetic sex of an individual is actually determined at fertilization, and those zygotes with two X chromosomes for the 23rd pair are genetically female, while those with XY chromosomes are male. Developmentally, the genitalia are not distinguishable as male or female until the 7th week of gestational development. There are occasional chromosomal aberrations in the 23rd pair that lead to developmental conditions, including individuals that have only one or three 23rd chromosomes instead of the usual pair. In addition to these conditions, the hormones that influence the gonadal primordia to become male or female sometimes fail to exert adequate influence. Consequently, occasional individuals are born with genitals that are sexually indifferent, not clearly male and not clearly female. Surgical and hormonal therapies have been instituted for these individuals with varied success.
Hi, I'm Mike Shively, and welcome to Introduction to Anatomy and Physiology. Today we're going to talk about female reproductive system. Let's start with just going around the room here and making a list of parts. I'll do the first one. How about ovary? How many of those would a typical female have? Two, right? Amber, what would be next? What would you think of next in female reproductive system?
The ovum, egg.
Ovum, egg, okay, it's a product of the ovary, and the ovary also produces a couple of hormonal products, doesn't it? What are the two main hormones produced by ovaries? Somebody? Adam?
Estrogen and progesterone.
Estrogen and progesterone, both very important hormones in the female reproductive cycle. Bryce, what do you think of as far as female reproductive components?
The uterine tube.
Uterine tube. Now, out on the streets, what is uterine tube usually called? Fallopian tube, after Gabriel Falloppii. And remember, we talked about anatomic nomenclature at the very beginning of this course and said that eponyms or proper names were no longer in vogue because they lack instructional and descriptive value. Uterine tube is very descriptive of that particular structure, although students do have to be careful because it sounds like from its name it may be part of the uterus rather than just connecting to the uterus, and it is an organ in and of its own right. Eva, what do you think of?
Well, if we're following the path of an ovum still, I think next in line would probably be the uterus.
Uterus.
Then.
Uterus, okay. And what kind of things does the uterus do? I mean, it has some functional responsibilities here in reproduction.
It carries the fetus during development.
So it's going to house and protect this developing conceptus, huh?
Mm-hmm.
And ultimately reject it whenever its wall gets stretched beyond what the uterus feels comfortable with. Does it transport anything?
Transport sperm.
Transport sperm, doesn't it?
Right.
Does. Sperm have to go through the uterus because the typical site of fertilization is not the uterus itself, but in fact is the uterine tube, i.e. fallopian tube that Bryce mentioned. What else? Susan, what do you think of?
Next would be the vagina.
Vagina. That's female copulatory organ, isn't it? It receives the erect penis of a male during sexual intercourse. And then there's a whole bunch of either external or almost external female genitalia. And that can be collectively umbrellaed by a single term. Does anybody know the single term from your reading? Adam?
The vulva?
Yeah, let's put that word up here for everybody to see. Vulva, V-U-L-V-A, is a name that encompasses a bunch of structures that are either external or almost external in the female reproductive system. There's a Latin equivalent of vulva, and it's pudendum femininum. So we can say vulva or we can say pudendum femininum. And we probably ought to list the kinds of structures that we're talking about. And I'll start. That includes things like major labia, which are skin folds, minor labia, which are folds of mucosa, mucous membrane. It includes the clitoris. Vulva includes the clitoris, which is a female counterpart of the penis. And under the concept or umbrella of vulva, we also have vestibular glands. These used to be more popularly called Bartholin's glands, the major vestibular glands did, and they kind of have the same purpose in a female that bulbourethral gland does in a male. And what was that, Starley?
Oh, to lubricate?
For purposes of lubrication. During sexual excitement in females, the secretion of the vestibular glands actually lubricates the vulvar area of a female prior to intromission of the penis. And then also included under vulva, we have vestibular bulbs and even the mons pubis. Vestibular bulbs are erectile tissue located in the lateral walls of the vaginal vestibule, which is kind of where the vagina opens. And the, what else did I just mention?
Mons pubis.
Oh yeah, mons pubis. The fat pad that's in front of the pubic symphysis is usually included under vulva or pudendum femininum. Let me put that other term up. Let's go to the overhead camera. Vulva is the same thing as pudendum femininum. Now I know we just blew through those things. We're going to take a look at them on some models here. Pudendum femininum. Well, let's bring up a plastic model here and look at some of these structures. So we'll go to the overhead camera. I'll put it on the front desk here, and we'll look at the structures. The camera can come down on it from above. Here we've got a mid-sagittal section through a bottom end of the trunk of a female, and we've got the ovary on this side is right here. I can pull up this part of the viscera. The ovary is right here. It's a relatively small organ, and then the end of the uterine tube is this kind of red structure right in this region. It's dilated and partially surrounds the ovary. That particular end we'll find in a little bit is called the infundibulum of the uterine tube. And then the uterine tube itself follows around this way and actually attaches to the horn of the uterus. So the uterus is right here, and that's the horn of the uterus, right there where that tube is attaching. The other one from the other side comes in from this direction over here. Then once I've pulled this off, we can go down here now and see the uterus itself in sectional view. And then this is the vagina. Now we didn't list cervix separately because the cervix is actually part of the uterus. Its full name is cervix of the uterus, to distinguish it from several other necks, if you will, of various bones. And even the neck, the front part of our neck is called the cervix. It connects our head onto our trunk. So this is the cervix of the uterus, which is the neck of the uterus in English, actually. The vagina itself, you can see, has these little folds, vaginal rugae, they're called, that allow the total length of the vagina to increase when sexual intercourse occurs. So this, a vagina that has nothing in it is relatively short, only 2 or 3 inches long. But when a penis is in there, these folds will expand, if you will, longitudinally to accept the length of the penis. Then if we come on out, you can see these 2 folds right here. This smaller inner one is the minor labium, if you will, on that side. And it's a mucosal fold, mucous membrane fold. And then this skin fold out here is the major labium on that side. Now if I put these parts back up here, get this thing reassembled a little bit, then we can see some of the external genitalia a little bit. This is the clitoris. Let me roll this up for the camera just a bit and get a pointer here. This is the clitoris, and its erectile tissue extends back along the side of the vaginal vestibule. And this is the vestibular bulb. It's erectile tissue. It kind of corresponds, if you will, to the erectile tissue within the penis of the male, has the same general structure. Finally, back here, This is major vestibular gland, and that's the duct thereof. And of course, this vestibular bulb and the major vestibular gland have contralateral counterparts on the other side. They're paired structures. The clitoris itself is a single structure, but it has left and right crura, like the penis of the male. And so this is the crus on this side. This would be the left crus of the clitoris, and there'd be another one on the other side. So that's kind of a quick run-through. I guess we didn't mention mons pubis, this fat pad out here. We stay on the overhead camera for just a second. This is fat that's in front of the pubic symphysis, mons pubis. It's called M-O-N-S pubis. So that's a quick run-through on a model showing those structures. Let me bring up another model that will allow us to kind of look right into the vulvar area. If you go to the overhead camera now, these are the major labia on this model here. And then just inside those, I can pull this will come apart. These are the minor labia in here, the mucous membrane folds. Of course, back here, this is actually the anus, or the opening, you know, from the anal canal, this position right here. Are there any questions about the overall layout on those parts? Let's go to a graphic that summarizes the female reproductive components that we've just gone over. There are 2 ovaries, left and right, 2 uterine tubes, left and right, single uterus, a single vagina, and then again, vulva or pudendum femininum is the term that was developed to encompass all of those other structures. I don't know if I made myself clear about vaginal vestibule. Let me bring a model back up to this overhead camera one more time. Again, this is the vagina from here to here. Okay, this basically is the vagina in this region between my finger and the pin here. The vaginal vestibule is this region right in here, kind of between the left and right minor labia. And the opening of the vagina comes out into there. And then you can see here, this is the urinary bladder right here, and the urethra coming down. You can see how short the urethra is in a female. And that urethra actually opens into the vaginal vestibule area as well. So the 2 openings are relatively close together here at the bottom of this model, opening of the urethra in this position and the opening of the vagina at that position, both opening again into the vaginal vestibule. Any questions about that quick run through on parts? We're obviously going to take those parts and talk about them individually and separately, but I just want to get the parts kind of listed before we began. Starla, you look like you have a question.
Sorry, I'm just wondering, with pudendum femininum, how does that break down into vulva?
You know, I'm not sure what the derivation of those words are, so I just can't remember the Latin that well. I'm sure there's a connection, though. It may be, quite often, though, the connection is a little far-fetched. Sometimes, you know, you say, well, why was it called that? And then you hear the Latin term, you say, oh, okay, but they were kind of going around Robin's Hood barn, weren't they, to come up with that name, and that may be true. In some cases, it often is. All right, what about the functions? Okay, so we got some parts here. What about the overall functions? Conceptually, what does the female reproductive system do? And I don't want you to say, well, it does reproduction. What does it do? Susan?
Well, first of all, it produces the ovum. That
produces an ovum, okay, right, by the process that's a process that's kind of parallel to what we talked about in the male. We called that process in the male spermatogenesis. In the female, we're going to call it oogenesis. Oogenesis. So ova production, or production of eggs, if you will. We often call ova eggs. And what else? Adam, what else does the female reproductive system do?
Provides copulatory facilities for women.
Right. Female reproductive system functions in sexual intercourse. So that's obviously a predominant function. What about another one, Eva?
Same thing I said before, carries the developing conceptus.
Gonna house and protect the developing conceptus, isn't it? protect it, house it and protect it for a while, and ultimately reject it. You know, when the uterine contractions at the end of gestation start occurring, then that's the uterus's way to just say no more. You know, I've had enough here, and it's time for you to go out on your own and meet the world. Susan, did you have one?
Well, the other thing it does is produces hormones.
Yeah, we mentioned that a while ago when we were listing some of the parts and so forth. Certainly produces the estrogens and progesterones that are so important to the female reproductive cycle. And then something we've all been through as individuals, and some of you have been through as mothers. What, Adam? The process of birth. Certainly that the ultimate rejection of that malignant phytoma, if you want to go that way, is the process that we commonly call birth, isn't it? And we've all been through that individually, certainly. Let's take a look at a graphic that summarizes the functions of the female reproductive system and see if we got everything mentioned that we have on this graphic. Production of ova, production of female sex hormones, copulation. We didn't specifically say fertilization, but actually female reproductive viscera are important in actually getting the sperm transported up to where the ova are. And when we talk about ovulation and so forth after a bit, we're going to mention why ovulation basically hardly ever occurs in the uterus itself, and certainly doesn't occur in the vagina. Protection of the developing conceptus, and then ultimately rejection of that conceptus at the process we call birth. So those are the major functions of the female reproductive system. I think they're probably philosophically self-evident to most of us when we see them listed there. I want to begin our discussion of the female reproductive system by spending a little bit of time on oogenesis. So we'll talk about oogenesis, and then we'll go into the ovary itself. And so we'll go to the overhead camera. What I want to do is diagram the process of oogenesis. The stem cells, the female sexual stem cells, are called oogonia. Now, what were they called in male?
Spermatogonia.
Spermatogonia. So these are the stem cells, if you will. Sexual stem cells. And of course, they are 2N. They're diploid. They have 46 chromosomes. Now, oogonia divide by mitosis. And their daughter cells, some of their daughter cells actually become primary oocytes. And this, since this was mitosis, I want to write it kind of small here. How many chromosomes are these primary oocytes going to have?
46.
46. They're going to be 2N. That's those regular nuclear division here with mitosis. So primary oocytes are 2N. Primary oocytes divide by the first meiotic division, to form a pretty good sized cell and a little teeny tiny cell over here. This pretty good sized cell is a secondary oocyte. And this little teeny tiny cell is called a first polar body. Now, does anybody have any idea what the physiological reason for this unequal division? We've got a great big cell and a little teeny tiny cell. This was first meiosis, meiosis 1. Remember, meiosis is a two-divisional process. What's the deal here? Eva?
Well, the polar body really isn't going to turn into anything that's needed, and so isn't most of the cytoplasm and the organelles and things just kind of retained in the ovum so that they can be used for energy?
In other words, the reason this division looks so unequal is because this secondary oocyte is retaining most of the cytoplasm, most of the organelles. Well, then why even have, what's the purpose of the division here? What's happening? Adam?
Splits the chromosome number in half.
That's right. In other words, first meiotic division reduces the chromosome number down to half. So 23 chromosomes go into the first polar body, and 23 go into the secondary oocyte. And so that's the purpose of a first polar body, really, is to get rid of 23 chromosomes without losing very much in the way of cytoplasm or organelles. All right. Interesting thing about secondary oocyte. This is what is ovulated. And if a sperm, and this is what a sperm actually penetrates, is a secondary oocyte. It's actually started its second meiotic division, but it's not completed its second meiotic division as yet. If a sperm does not penetrate through that secondary oocyte, the secondary oocyte will never complete its second meiotic division. It will degenerate after a day or two and be lost, be gone, break down. But if a sperm does penetrate, if it is fertilized, then the secondary oocyte completes its second meiotic division. So let's go back to the overhead camera, and we'll put a little sperm here and say he's going to actually penetrate through into the cytoplasm. Once he penetrates into the cytoplasm, the secondary oocyte completes the second meiotic division. Now the sperm pronucleus sits over here on the sidelines and waits for the secondary oocyte to complete that second meiotic division. It's kind of like he's going to pick up his prom date and she's not ready yet, so he gets in there and has to sit in the living room and talk to Dad for a while, okay? So here he is waiting while the secondary oocyte completes that second meiotic division. And when it does that, stimulated by the penetration of the sperm, it kicks off what's called a second polar body. That's to get rid of the second copy of DNA within each of the 23 chromosomes that it retained after this first meiotic division. And the final cell here is called, in the business, it's called a definitive ovum. Now the definitive ovum doesn't last very long, because immediately then, as soon as it gets rid of this second polar body, the 23 chromosomes from the sperm combine with the 23 single copy DNA chromosomes that are retained after the second meiotic division, and the thing immediately becomes a zygote, which is the name that we use for a fertilized ovum. So the definitive ovum, you know, it's there for a split second in practicality, because immediately when the second polar body is kicked off, getting rid of those second copy of each of the 23 chromosomes, second copy of the DNA within each of the 23, then the sperm pronucleus unites with the definitive ovum nucleus, and we have fertilized ovum, we have a zygote. And of course the zygote is 2N again, kind of running out of room. This guy's 2N. Secondary oocyte, of course, was just N. And the definitive ovum technically is just N, although sitting there waiting to combine with it are the other 23 chromosomes coming in from the male. So hopefully, if you take a look at this whole diagram, you understand that half of your or my genetic material, half of our DNA came from Mom, and half of that material came from Dad. Bryce?
So when the stem cell divides, it becomes two primary oocytes?
Okay, some of these daughter cells up here can go back and become other oogonia. So this mitotic process that occurs here increases the number of oogonia. Some of those oogonia then differentiate out to become primary oocytes. Same thing we were talking about in a previous episode with the spermatogonia and the primary spermatocytes. Exactly the same thing.
Okay.
All right, anyway, that's the general process. Now, I want you to notice that if you take a look at the scheme that you've drawn there, starting up here with a primary oocyte, we only get one definitive female sex cell out of each process of oogenesis. Remember when we talked about the process of spermatogenesis, how when that process occurred, we get 4 sperm from each primary spermatocyte, but there's only one definitive ovum that's derived from each primary oocyte. Starley?
Sorry, I was just wondering how twins play into this.
Okay, it's an interesting concept. Now, there's 2 ways that twins can occur. Let me erase this, but let's stay on the overhead camera for just a second. Let's call it multiple births because this will apply to triplets and quadruplets and so forth. We can have what are called monozygotic. Let's just entitle this again, multiple births. Monozygotic implies this, Starley. We got down to the zygote, the fertilized ovum, and of course after about 24 hours, this zygote is going to divide mitotically to form 2 cells. And then in less than 24 hours, those each divide, and we end up with what we call the 4-cell stage of development, and then we go to 8, and so forth and so on. You can do the math. It doubles for a while. If we're talking about monozygotic or identical twins, triplets, quadruplets, or whatever, what actually happens is that sometime we only had one fertilization that occurred. There was 1 sperm and 1 ovum originally, but sometime during this early first few divisions, the cell masses divided themselves. Perhaps at the 2-cell stage, these split and became 2 different cells, both of which developed into a complete individual. Perhaps the split occurred right here in the 4-cell stage, and these 2 cells became 1, and these 2 cells became 1. And hopefully you can see that these are going to be identical because they all have exactly the same genetic material. DNA is all identical, right? On the other hand, we have dizygotic or multiple zygotic twins. Fraternal type twins, they don't even have to be the same sex. The implication here is that there was multiple fertilizations. There was more than 1 ovum ovulated. And multiple fertilizations. Now, there's all kinds of permutations and combinations of this that you can have. Let's say we got a set of triplets. We could have in that set of triplets a set of identical twins and then somebody else, that might not even be the same sex. Or might be the same sex but look different, have different color hair and eyes, and obviously the only thing they'd have in common is they had the same parents and the same birthday. Other than that, they're not related any closer than any other brother and sister in the same family. Susan?
Why is it with artificial insemination and with other fertility methods that the incidence of multiple birth is so much greater?
Many of the drugs that are given for fertility problems in females actually cause multiple ovulations. They're hormonal influences that actually cause more than 1 ovum to be ovulated. So you have multiple possibilities for fertilization. That's the way that happens. Eva?
How late in development can that split in monozygotic twins happen? I mean, you're not going to get along to about 2 or 3 months and suddenly pop up with
it has to happen pretty early, but I don't think it has to happen just at the 2-cell stage. We can be further along, but it has to be relatively early because after we start getting very many cells, then the cells themselves start undergoing some differentiation. But very early in development, in the early forms that we call cleavage, in the very early development, when we have the first initial divisions, those cells can separate.
Before it ever implants in the uterine wall, right?
This typically is going to happen before implantation, yes. And after fertilization until implantation can be maybe 5, 6, or 7 days. Quite often 5 is quite typical. But during that time there will be several divisions that will have occurred. So, Adam?
If there are multiple ovum ovulated, but only one is fertilized at a given point, do the others remain viable for any length of time?
No, ova will degenerate usually within about 2 days. They're viable under ideal conditions in the female reproductive tract for a couple of days, give or take a few hours. And then they degenerate to the place that even if a sperm penetrates or tries to penetrate, they won't accept sperm. They're starting to break down. Starley?
Sorry, when you have like Siamese twins where they're connected, is the eggs they actually separated and then they didn't fully get away from each other?
Yeah, well, it depends on exactly where they're connected and how they're connected, but that's the idea, is that late in development there was some kind of fusion of the tissues that occurs. And I don't know if trauma plays a significant role in that or not, but I would suspect there may be some trauma involved in it. Eva?
Sorry, just one more question from me. Is it possible for multiple sperm to fertilize one ovum?
In general, no. And I'll show you why here. Let's go to the overhead camera. Here sits a secondary oocyte, and after ovulation there's a bunch of friends that kind of go along for the ride called corona radiata cells. There's kind of a thick membrane in here around the, again, secondary oocyte. I'm just going to call it an ovum. Now, here comes a whole herd of sperm, right? Yeah.
Well, yeah.
They're on a stampede. They're close enough now to where the chemotaxis is kicking in, and they're going to go over. He's like the little boy looking for the pony in the pile of manure. You know, he figures, he's the eternal optimist. He figures there's got to be a horse in there somewhere. So these guys are headed over here, being drawn by a certain chemical, and they get real close. There's actually a material that's in the skull cap, if you will, of the sperm, a little structure called the acrosome, that is involved in chewing through this thick membrane. And it'll actually allow one sperm to penetrate through. But as soon as that happens, somehow there's a chemical change in the whole membrane around here that prevents other sperm from being able to get through. It's kind of like once one person goes through the door locks behind them. But in answer to your question, now what if, in theory, what if there was another one attacking over here, you know, at exactly the same time? You know, and obviously it takes some kind of a split nanosecond for this chemical change to get all the way around. I honestly don't know. I think there have been some cases where there certainly have been some possibilities of that, but in general, no. And one of the interesting things about human development is that we don't end up messed up more often than we do when you think of how complex the whole process is. Susan?
Along with Eva's question, once the DNA and RNA started to go together and combine to make the unique set of DNA from each parent, wouldn't that eliminate the extra sperm?
Yeah, he'd be an odd man out, wouldn't he?
I would think so.
Or we'd have, you know, we'd have a 3N individual, which
And that wouldn't be viable, would it?
probably wouldn't be
No,
viable.
usually.
You know, and it may be that that's exactly what happens in a few cases. Those of you who have tried to get pregnant know that when you're trying to get pregnant, it doesn't seem to work, and if you don't want to get pregnant, you know, it kind of happens at the drop of a hat.
Yeah.
But it may be that some of that does occur, and there's just no viability for whatever reason
Yeah.
in that quote zygote. Bryce?
In another session, you said that only about 50% of the sperm are motile. So are those the only ones that can induce
Yeah,
fertilization?
if a sperm is not wiggling in its tail, when you look at it, you know, through a microscope, that sperm is not going to be able to do its job as far as it's not moving. You know, it's kind of like the fish is dead now. And so it's not going to be able to do its job as far as releasing the chemical from that acrosome that penetrates through that thickened membrane. All right, let's talk about ovaries a little bit. And let's go to the overhead camera. And we'll kind of draw an ovary. Of course, I use the same drawing for testis, you know. It just depends on. Actually, I think when I was in the first grade, I put some things like this around it, and we called it a sun, but I don't remember. All right. The ovary sits in the abdominal cavity. There's a left one and a right one. And they are enveloped by peritoneum, just like testis is in its original development. So there's actually a peritoneal investure around here. And this would be visceral peritoneum, that serous membrane that covers everything. Blood vessels and nerves come in over here in a little area called the hilum. As the follicles, the female sex cells and their surrounding friends develop within this ovary, once they reach maturity, they have to actually break through this peritoneum. First, there's an inner shell of connective tissue proper, and that's called the tunica albuginea of the ovary. There's that tunica albuginea again. So let's let this black line represent tunica albuginea of the ovary. And then the red will be the visceral peritoneum on the outside. So those are the two things that have to be penetrated at ovulation. Now the ovary contains hundreds of what are called primary follicles, primordial follicles. And these are female sex cells that are arrested in their development, and they're simply waiting to continue their development and actually become ovulated, become part of a reproductive cycle in a female. As those female sex cells get close to ovulation, they actually enlarge and have a surrounding bunch of cells around them and actually sit in kind of a fluid-filled pocket within the ovary. So I've drawn this enlarged, but this whole thing would be like a little spot right there within that particular ovary. And this is a vesicular or a mature follicle, sometimes called a tertiary follicle. This is the secondary oocyte right in here. And these are follicular cells that are surrounding it. These are other follicular cells out here. And this space is sometimes called the follicular antrum, is filled with a fluid that's got a name too that I don't care if you remember. It's called liquor folliculi. At any rate, let's suppose that this one it's about time for it to ovulate. Then the fluid within here becomes very heavily saturated with estrogen because these follicular cells begin secreting estrogen near ovulation, leading up to ovulation. So estrogen is the hormone that is highest just before ovulation. So there'll be a lot of estrogen in there, in that fluid. When ovulation actually occurs, and that depends not only on the estrogen that's developed in there, but it also depends on a hormone from the pituitary gland called luteinizing hormone, LH. Both of these are involved in the ovulation process. When ovulation actually occurs, the oocyte, secondary oocyte, and these follicular cells break through the surface of the ovary. They go through the tunica albuginea and they go through the visceral peritoneum. And let's just go over here since I've got more space on this side. And let's say this broke through, and now we are out here with that cell and those follicular cells surrounding it. It's actually kind of free in the peritoneal cavity, a little subdivision of the peritoneal cavity of females called the ovarian bursa, but surrounding the end of the ovary, and partially actually around the whole ovary, doesn't go all the way around the whole thing, we've got the dilated end of the uterine tube. So this is the uterine tube. And this dilated portion, kind of like a great big catcher's mitt around the ovary, is the infundibulum of the uterine tube. I'm going to write U period T for infundibulum of uterine tube. Most of the ova that are ovulated are, quote, captured, if you will, by the infundibulum of the uterine tube, and then ciliary action, the lining of the uterine tube is ciliated, starts sweeping this ovum slowly but surely down the uterine tube, and of course down here eventually we'll get to the uterus. Now it's only a few centimeters down the uterine tube to the uterus, but the ciliary action sweeping this ovulated ovum takes a couple of days. Takes a couple of days, about 48 hours plus or minus, to get this down to the uterus. It's kind of interesting. This female sex cell is only fertilizable for about 2 days. It's only got a viable life of about 2 days. As a consequence, if it's not fertilized within the uterine tube, it probably will not be fertilized, because by the time it gets all the way down to the uterus, even if it meets sperm down there, it will not be reproductively viable. Eva?
I'm just wondering, since the cilia are pushing the ovum down, doesn't that kind of make a countercurrent for the sperm to have to?
Sperm got an
fight
uphill
against?
battle, don't they? That's one of the reasons why so many, many are sent, but few reach the destination, Actually, sperm, meanwhile, are being transported up the uterine tube in a sexually active female, not using barrier-type contraceptives anyway. Sperm will be actively transported up the uterine tube at the same time that these ova are being transported down. And how can that possibly happen? Well, the sperm are really tiny cells, and the ova and those surrounding cells called corona radiata cells at this point, used to be follicular cells, that makes a pretty big mass. Okay? You can actually see one of these with your naked eye. You can't come close to seeing a sperm with your naked eye. Okay? Well, what happens is peristaltic action, smooth muscle contractions within the wall of the uterine tube, actually move the sperm up at the same time the cilia are sweeping the ova down. I'm trying to think of a parallel illustration. Let's imagine you're trying to sweep out your garage on a windy day, okay? So the wind is kind of blowing all the trash back into the garage. You're sweeping. You won't have any trouble with the broom straws catching the leaves and the big stuff, right? The big chunks of wood and stuff like that. You can sweep those out. But the real fine dirt, if the wind is blowing, it'll take that really small stuff right through those broom straws. And if you think of the cilia here as being the broom straws, the cilia can move the big thing, which is the ovum, down at the same time that the sperm are being peristalted up against the cilia. Does that make sense?
It does.
So that's actually how that happens. So that because of this 2-day viability, let's go back to the overhead camera, because of the 2-day viability of the ovum once it's ovulated, if fertilization doesn't occur in this next 2 days, it's not going to happen. And for that reason, we say the uterine tube is the typical or usual site of fertilization simply because of the 2-day journey that it takes. Bryce?
You said that the top of the infundibulum is open, so does that allow any ovum to escape into the peritoneal cavity?
In other words, let's suppose that ovulation occurred clear up here someplace and this ovum from some reason snuck out. Decided, I don't want to go down and meet any sperm. I want to see what it's like up here in the main part of the peritoneal cavity. You know, that does happen once in a while. Matter of fact, sperm are all, you know, sperm get shot up here by peristalsis, and they're out there running around all the time in the peritoneal cavity of females that are, again, sexually active using non-barrier contraception. Sometimes fertilization can occur, and then the fertilized ovum, the zygote, will sneak out the open end rather than journeying down here. Now, most of the time, not a happy place to set up housekeeping is not found out in the peritoneal cavity. So this probably happens quite a bit, and they're lost and never heard from again. But when we get an established pregnancy someplace other than the uterus, we call that situation an ectopic pregnancy. And there was an ectopic pregnancy out in the peritoneal cavity that was carried to term a few years ago and actually delivered by cesarean section, of course, up here in the University of Utah Medical Center. And that individual, the conceptus had actually established a placenta of sorts out on the omentum and was carried to term, and then obviously had to be delivered by C-section. The more usual site of ectopic pregnancy, Bryce, is within the uterine tube. Instead of making it all the way down to the uterus before it implants, every once in a while a fertilized ovum will implant someplace along the course of the uterine tube. And when that happens, sometimes we call that a tubal pregnancy. When that happens, development proceeds for a while, but then the uterine tube has a very thin wall, has the inability to expand sufficiently, and so as the conceptus gets larger and larger, the mother notices pain, goes in, you know, if they do a sonogram, they find this tubal thing, they'll typically medically abort those simply because the tube is going to blow eventually. And when it does, by the time it does, the blood supply will be so richly established that there's a real danger of fatal hemorrhage for the mother. I think there have been some cases where, you know, individuals who were obviously anti-abortion, which a lot of folks certainly would be, that they tried to maintain that tubal pregnancy for a while. I don't know if there have been attempts to move the tubal pregnancy down into the uterus or not. I don't know if that's ever been successfully done. But I do know this situation I was talking about, this ectopic pregnancy out in the peritoneal cavity, that's the only one in medical history that has happened, that's been brought to term and delivered. So, Starley?
Does that cilia move all the way down the uterine tube?
Yeah, cilia, the whole uterine tube is ciliated.
So with those tubal pregnancies, it's actually just kind of not being pushed?
Yeah, haven't you ever been sweeping something out of the garage and it got hung up on a little crack in the concrete, you know, and you had to get down there with a paint scraper and scrape it off. Find out, well, no wonder, it's bubble gum, you know. It won't. So every once in a while, a fertilized ovum will just get stuck someplace on the way down and decide to implant there. Implantation, incidentally, is a term that we use for when the early conceptus, usually obviously at a multiple cell stage, actually sticks, you know, typically to the uterine wall and actually becomes physically attached. Another word for that is nidation. Implantation is more commonly used, but nidation refers to the same thing. Any other questions about that? Susan?
I have a quick question. The primary follicles, when we were talking about oogenesis, you said that this at the primary split, that one of them can go back, does it make another follicle?
No. When we were talking about oogenesis, we said oogonium. When it
Right.
divides mitotically, some of those daughter cells can just become more oogonia.
But not
But some of the no. The follicle is going to
Okay.
be, follicles basically are secondary oocytes arrested in the second meiotic division, sitting there in various stages of development, but arrested in the second meiotic division.
Okay. So do women, are they born with a certain number of possibilities for?
Yes, it's a very large number, but there is a finite number of possibilities.
That's what's
basically.
confusing me
Then
about
what
this.
will happen is only X number of those. Let's say you're never pregnant, okay? So you're going to cycle about 12 times a year.
Right.
You're going to ovulate about 12 times a year. Most of the time, it's just a single ovum that ovulates. Sometimes we have multiple ova that ovulate, as we mentioned a while ago. So you do the math. If you're 12 times a year, and if you have a 40-year reproductive cycle, you know, or 35-year reproductive life, you know, from puberty until menopause, then, you know, you have 12 times 35 or 40 ova that do develop, you know, do ovulate and have the possibility of becoming individuals. Now, when we talk about menopause a little later, perhaps in the next session, we're going to talk about the fact that if you have a lot of children, you're probably going to be reproductively viable for another year or two or three than somebody who has no children, a woman that has no children, simply because when you are gestating, you don't go, your ovaries quit cycling and you don't ovulate. Every time you ovulate, there's scarring that occurs in the ovary.
Okay.
So if you have a lot of children, if you're pregnant a significant portion, you know, of your life, then you'll have fewer scars by the time you're, say, 40 or 45 in your ovaries than will the next person who has not been pregnant very many times or no times in their life. Does that make sense?
Right, so the scarring is the limiting factor here, not so much how many ova you're born
Right.
with or
The
whatever.
scarring
Okay.
seems to be the limiting factor. Let's talk
Okay.
about that just a little bit in the little bit of time we have remaining. Let's go back to the overhead camera. And when ovulation occurs, there's actually a little bit of hemorrhage that occurs into the space. So basically ovulation occurs, there's a little bit of blood that occurs right in here. And when that happens, a histologist will look at that and call that corpus hemorrhagicum, which literally means bloody body. Let's see, I think I left an R out. Corpus hemorrhagicum, bloody body. Now this has nothing to do with menstrual flow. Has nothing to do. This is basically happening, you know, a couple of weeks after the onset of menstruation. So this is happening right after ovulation. This is the initial, quote, scar, if you will, from whence ovulation occurred. The surrounding cells in the next couple of days undergo luteinization under the influence of the hormone LH, which also was involved in the ovulation process, and they begin producing progesterone. Right before ovulation, these cells produced estrogen. Right after ovulation, they produce progesterone for several days. So the estrogen levels rise, then ovulation occurs, and then the progesterone levels rise, and the estrogen levels drop down. And so we have this estrogen, progesterone, rise and fall, rise and fall. At any rate, whenever the cells go into progesterone production big time, they take on a yellowish color and are called the corpus luteum. So at first it's a corpus hemorrhagicum, then it's a corpus luteum. And corpus means body, lutea in Latin means yellow. Corpus hemorrhagicum, bloody body, corpus luteum, yellow body. Then with more time, after several days, that actually gets replaced with scar tissue and becomes what's called a corpus albicans, which means white body. So this one, think of this one as a scar, a connective tissue proper scar. Think of when you think of a corpus luteum, think of progesterone production. I'm running out of room here. I'll just write progest. And this corpus hemorrhagicum is simply a little bit of hemorrhage that occurs because a bunch of cells were plucked out of the ovary at ovulation along with the ovum. Okay? Any questions on that? So it's accumulation of these, Susan, these corpus albicans, these scars that we think eventually cause so much connective tissue development within the ovary that it begins to interfere with the normal cycling process and brings on menopause.
Okay.
Amber?
I've heard that with athletes, with women athletes, they'll miss their menstrual cycle by sometimes a month, a couple months. What causes that?
Okay, let's talk about, we haven't talked about the ovarian cycle per se yet and all, but you don't cycle until puberty, right, ladies? You don't cycle while you're pregnant, and you don't cycle after menopause, after the cessation of ovarian cycling itself. So the other times that you might not cycle are during periods of extreme emotional or physical stress. Quite often, female athletes that are really training heavily will not cycle. And quite often, individuals that are under extreme emotional stress will not cycle either.
Does that mean that they don't?
They don't ovulate.
They don't ovulate.
Don't ovulate. Somehow, there's not enough luteinizing hormone released from the brain in order to cause the ovulation process to occur. So everything's just put on hold. We'll continue the female reproductive system next time.